Welcome to qnawire.
All right. We've got some sort of, I don't know the actual stereo configuration, but we've got 1,4-dimethylhexane and what is potentially an enantiomer. We're going to find out what the relationship between these molecules is. Okay. Does this initial molecule have stereocenters? Are any of the carbons in this initial molecule stereocenters? That's a good question to ask when you're looking at the relationship between uh, atoms that may be isomers of some kind, or molecules that may be isomers of some kind. Identifying stereocenters. So, I mean, we're shown that there's a wedge coming off this carbon. Does that mean it's a stereocenter? Not necessarily. So just because this is drawn with a wedge doesn't mean that it's a stereocenter. In fact, one could imagine flipping this molecule over, like if I held out my hand in front of me and then turned it over and pretended that this molecule like was my hand, it's going to look like this, right? And this may be a hint that there's something going on, like this is the same molecule but it has dashes instead of wedges, like, but not like it's an isomer. This would be the exact same molecule, we just flipped it over. The other thing you consider is that to be a stereocenter, a carbon needs to have bonds to 4 different things, right? So if we look at this carbon, right, we've got a bond to a methyl, a bond to a hydrogen, and then a bond to a CH2, bond to a CH2. And then we'll just keep, for now they seem the same. They're both CH2s. But we got to keep going around the ring to see if at some point they'll become different, right? So we keep going this way, we keep going this way, and oh, it's another CH2, and it's another CH2. So far, each of these paths is identical, right? Then we go one more carbon, and we're at the same carbon. These two carbon bonds, like specifically this bond and this bond, are identical. This isn't a stereocenter. It's not bound to 4 different things. It's bound to a methyl, a hydrogen, and then it has 2 identical bonds. So this is not a stereocenter, and this is not a stereocenter. Okay, I just wanted to point that out. So then when we look at what the relationship between this molecule and this molecule are, uh, you know, they can't, in fact, be enantiomers, right? You can't have an enantiomer if you don't have uh, any stereochemistry going on, right? Consider this molecule as well. You'll find that this molecule similarly has no chiral centers. We can really just step through the same process as we did with the molecule to the left. So really, what relates them or defines them is that the methyl groups in the left-hand molecule are cis to each other in terms of the ring, whereas in the right-hand case, they are trans. So if anything, and I can't see what the drop-down options are, these are cis-trans isomers, but they aren't stereoisomers. They don't have any stereogenic carbons. Okay. So hopefully cis-trans isomer is an option. Otherwise, maybe no relation could be an option. But let's continue. All right. Now, got this dibromobutane. And this dibromobutane. Well, there's a couple different ways we could go about telling these apart or determining the relationship between these. One is to just determine what the stereochemistry of each stereocenter in the molecules are, right? So if I throw a hydrogen back here and a hydrogen back here, then I can label the substituents in order of I'm forgetting the word. Using the Kohn-Ingold Prelog rules, order them in terms of priority, and then determine, whether it's clockwise or counterclockwise, going from 1 to 2 to 3. This is clockwise, so this is R. And then I can do a similar thing for this stereocenter. Bromine's the highest priority. The carbon with the bond of the bromine is the next highest priority, and the third highest is just the methyl group. The least is in the back, and this is also clockwise, so this is R. Okay. Now, if I do the same over here, I put in the implicit hydrogen explicitly. And I mean, right away I can tell, it is the case that if you switch a wedge to a dash and a dash to a wedge, you will totally invert the stereochemistry of that group. So without even stepping through it, I know that this is S and that this is S, right? So we've gone from an RR compound to an SS compound. If you've got a compound in which every R turned into an S and every S turned into an R, as in every stereochemical designation is flipped exactly, those are enantiomers. Right? So if I had like 3R, 4S, 5R, 6R, some random molecule, and then I found another molecule that was the same thing, but it was 3S, 4R, 5S, 6S, they would be enantiomers. I wouldn't have to really work through it, just so long as the connectivity is the same and every stereocenter changed from R to S or S to R, respectively. Now, the other option with this is to, let me redraw it real quick. You don't have to watch the rest of this if you don't want. You already have the answer, at least they're enantiomers. We got the bromine here. Get the bromine here. Now, it's not obvious, I think, the way that this second molecule is drawn, but consider if I could rotate it into the page 180 degrees, such that this bromine would now be facing me, and this hydrogen would now be away from me. This carbon would be on the right-hand side of the molecule, and this carbon would be on the left-hand side of the molecule. Okay, so let's even just call this carbon 1, 2, 3, 4. So I should start like this, 4, 3, 2, 1, right? Because I'm going to rotate it into the page so the 4 is on the left and 1's on the right. Okay, and then I know that on carbon 2, there's going to be a bromine facing me. And on carbon 3, there's going to be a bromine facing to me. So a wedge to bromine on carbon 2 and a wedge to bromine on carbon 4 or carbon 3. Okay, let's transport that down here. This is carbon 4. Carbon 3, I knew there was going to be a wedge to bromine. Carbon 2, a wedge to bromine. Carbon 1, nothing. Now that I've redrawn this molecule, it may be slightly more obvious that it's a mirror image, a one-to-one mirror image of the first molecule, which is another way of saying or showing that they are enantiomers, right? So you can go through and determine the stereochemical designation and figure it out from there, or if you want to, you can kind of mentally step through what it would be like to rotate a molecule and just visually inspect them to see if they're enantiomers. All right.